Hello, I am doing this video as a follow-up to the last video I have uploaded under the title Uncountable Fatou's Lemma. This title of the video is quite misleading as I do not really give an answer to that question, although I give an explanation of why it is relevant to this. Thanks to a friend of mine who brought this to my attention, it could be disappointing for people who are looking for uncountable counterparts of Fatou's lemma and watch this video and don't find the answer that they want. So this video will hopefully clear that out, and I will in future, of course, correct the title of the videos and the thumbnails accordingly. So without further ado, let's dive into what we were looking for and what do we mean by an uncountable Fatou's lemma. I don't think it's called Fatou's lemma, but I couldn't come up with any standard universal name that is recognizable for the following fact from basic measure theory. So suppose A1, A2, and so on is a decreasing sequence of measurable subsets of R1, and Lebesgue measure is intended here, but this is actually a more general theorem that holds in many more types of measures, but we don't want to get into details of that, so I just want to state a true statement involving these. So there's a decreasing sequence of measurable subsets of R1, and measure of them is finite. So the first one, for example, being finite is enough. Then there are two claims. Number one, that the intersection of all of these sets is measurable again. And number two, the measure of this intersection is limit of the measure of the elements in the sequence. Okay, so that's a fact of life. It's the truth. Now, what I meant, so by calling it Fatou's lemma, I kind of mean this, although it requires a bit of imagination to see the connection. So what is the uncountable version of this? So what is my question? So I want to start with an arbitrary family of subsets. So alpha from some index set, be measurable subsets of say 0, 1. So that now the finiteness also is built into this. Now, how can we replace the point being that with gamma, possibly uncountable. Okay. And the replacement for this decreasing condition could be that for every alpha and alpha prime in the index set, either A alpha is contained in A alpha prime or A alpha prime is contained in A alpha. In other words, this collection of sets form a completely ordered collection of sets with respect to the inclusion relation. So are the following then true? The question is, so A prime, let's say, intersection of all of these sets is measurable. Is this true? b prime, the measure of this intersection is, well, how can we replace the limit there? Well, we had the decreasing sequence, so that was really limit infimum or just infimum. So we can naturally take infimum over all this index set. So this is, both of these are questions. So the question, all of this paragraph, is as follows. You have a collection of measurable sets, many of them, but with this chain property that each pair has this relation. What can we say about the full intersection? Is it measurable? And if it is measurable, is the measure of the intersection infimum of the measure of individual ones? So this is what I mean by an uncountable Fatow's lemma, or uncountable counterpart of the previous theorem that I wrote down. The previous video that I did was merely asking whether you can always. So the previous video had nothing to do with measures, but merely asking, is there always gamma prime subset of gamma with gamma prime countable and intersection of A alpha from gamma equal to intersection of A alpha belonging to gamma prime. In other words, can we always replace this arbitrary intersection with intersection of only countably many of them? And the connection would be that if yes, then answer to A prime and B prime is yes. But we showed in previous video that this cannot be true, that this cannot be true. So we showed that it's not always possible to replace uncountable number of intersections with countably many of them, because otherwise we could apply the theorem in the beginning of this lecture and then from that conclude everything, the parts A prime and B prime. And then we used Zorn's lemma to prove that this is impossible all the time, but that does not quite really answer our questions A prime and B prime. Maybe it's not possible to always replace with countable intersection, but still A prime and B prime end up being true. If you could replace this with a countable intersection, then A prime and B prime would follow. But we haven't ruled out that maybe the possibility of replacing with countable intersection, that is not necessary for A prime and B prime to be true. I hope I didn't confuse you with so many P implies Q arguments. But anyway, most likely the answer is no. I don't have an explicit example, but I found something very interesting on overleaf, and this is another bonus to this video that I'm doing, that I am introducing you to this Math Overflow website. I will do a separate video on Math Stack Exchange and Math Overflow and how to use them effectively and why you should use them, that they are good resources for sharing ideas and sometimes getting quick answers to stuff. So this question is very relevant and has been asked in 2012. And there are some good answers to it, multiple good answers to it. I must warn you that our chain condition here is not part of the assumptions. No one is dealing with the case of if the collection of sets have the chain property. But I believe that using ordinal numbers, it's almost, I'm not sure, but I can guess that there is no loss of generality in actually assuming you have the chain property, because Well, there's the standard technique that if you have countable, you can just start with A1 and replace A2 with A1 intersection with A2, and A3, original A3 is replaced by A1 intersection with A2 intersection with A3. So you move into a decreasing sequence while retaining the original full intersection. With uncountably many of them, maybe you can do the same, but you have to use some more abstract nonsense like ordinals and whatnot. Modulo that, if that is the case, if you do not lose generality by moving into chain property, then any negative answer to the full question is also a negative answer under the chain assumption. So let me read you to this question. So suppose this is an uncountable, so I is the index set here, the curly I. So you have for each element in I a set EI, and these are measurable sets with full measure. And this should remind you of the original video that I did, because there I also talked about sets with full measure in 0, 1. Sets, measurable sets whose measure is equal to 1 and are subsets of 0, 1. So a probability space is just a space with finite measure, or you can, without loss of generality, say that measure of the full space is equal to 1. So interval 0, 1 with the Lebesgue measure is an example of a probability space. Now you have an uncountable collection of subsets that are measurable. Each one is measurable and its measure is equal to 1. Now the question in here is, what can we say about the probability? Here will be just the measure of the full intersection. I know that the questioner is aware that I know that an uncountable intersection of measurable sets is not necessarily measurable. That answers our question A prime in the negative, although again the chain condition is not assumed here. But are there in general some general conditions that still allow such infinite intersections to be measurable? So the question is a bit vague, but after reading the answers I came to the conclusion that it's basically asking about this index set I. And some of the answers are like, if your indexing set I is not too huge, then probably you will still get that the full intersection is measurable, and also that its measure indeed also equals 1. So not surprisingly, this involves a lot of a lot of beyond basic set theory stuff. It has to deal with the continuum hypothesis, like what is the first uncountable, basically what happens after countable. Also the type of set theory axioms that you are using to begin with. So this question is intimately connected to such stuff. I'm not gonna delve into the details of these answers, which I have to confess I don't understand all of them, but I kind of see what's going on. With most likelihood, the answer to our questions A prime and B prime are in the negative, and I believe that firmly enough that I don't want to pursue this question really, to be honest. Okay, so one of the very nice answers I read was actually this one from Nick Weaver. And here's the theorem that he states. So we say a set A almost contains a set B if the part that it fails to contain is negligible, has measure 0. So we say one set is included in another set if up to a null set this is true. So we kind of relax our very definition of inclusion of set A being in B. So we are ready to just turn a blind eye to null sets. If we do this, then here's a beautiful theorem. Let EI, I from an indexing set, be a possibly uncountable family of measurable subsets of a probability space. then there is a measurable subset E of your space such that the following two things happen. One, E is almost contained in each EI. So in a sense, it's kind of the intersection of all of these sets, but this is not a precise claim, so what is meant is exactly what is written here. So that up to ignoring a null set, E is a subset of each and every one of these EI. And number two, E is like the biggest set with this property. If there is another set which is almost contained in every EI, then this E is almost contains that one, so it's bigger than that one. Of course, everything up to null sets. And there is the third claim, basically saying that this E is unique up to modifications by null sets, by adding or subtracting null sets. And this is a close to, not close really, but well, measure theoretically, yes, it is close to exactly what we needed and wanted. So yeah, so this type of beyond countable collection of sets is not a type of math I wish to deal with on a daily basis, but some people enjoy exactly that type of things. They get crazy big sets, but yeah, so hopefully this will further explain what I meant by Fatou's lemma and uncountable version of that. So the two videos together hopefully will complement each other. And if you find the answer, a definitive answer to this question, I very, very much would love to have you comment it below the video for everyone to enjoy. So again, with the most likelihood, the answer is no and no, but well, where is the proof? Thank you for your attention, and see you in a future video that will again involve some set theory stuff, but much more concrete one. And after that we will move into well, whatever we find beautiful and interesting. Thank you so much.